Hey everyone, I'm Anish and welcome to PrepFusion. So today we will be doing the lecture 12B, basically part B of the lecture 12. So in the part A, what we did basic theory and understanding of what is a similarity transform, why we do similarity transform and what we mean by similar matrix, and to what we do similarity transform and what things remains same even after doing the similarity transform to the state variables. Okay, so yeah, all those things we studied. I hope you have revised all those things. So basically, right, let me give you a quick overview of what we did. So when are two matrices similar? When A and B are similar, when the eigenvalues are same, right? Not the eigenvectors. Eigenvectors will change, and by what ratio they will change. I also have explained that also, by what factor. Also, right, will another thing be same? Yes, the number of vectors, independent eigenvectors, should be same, right? So yeah, those things we did. We took a few examples from there. We understood that what things, which matrices are similar and which aren't, right? And then yeah, these were the examples. Okay, these were the examples. And then here, right, I wrote the relation that I want to transform my I want to write my new vector, new state variable as this relation, right? Like this one, where x bar of t is my new state variable and x of t is my old state variable, right? So this is my relation. Okay, this is how I want to transform, right? So if I do this, then I put in this equation. Okay, then I get I do some intensive calculation and I get my new d bar as d only, c bar changes to cp, b bar changes to p inverse of b, a bar changes to p inverse ap, right? So yeah, this is what this the matrices changes. Okay, but do the whole overall system changes. Okay, do the whole overall system changes. So the overall system, right, this is just if I want to check transfer function, you know, the system transfer function should remain change whatever happens, right? It should not depend on the state variable. If the state variable which I choose, I change the state variables, right, which I choose. Okay, so after intensive proof and all those things, we got to know, yeah, transfer function will be same only, and characteristic equation, they will be also same because the poles of the transfer function will be same also. Okay, so this will be also same. Okay, proof it, this will be same. Then eigenvalues, yeah, if the characteristic equation is same, the eigenvalues will also be same because eigenvalues is basically equals to poles of the system and that is not changing, so they will also remain same. State transition matrix, this will change. Why? Because state variable is changing, that's why state transition matrix itself will change, right? To what factor it will change? It will change like this. Okay, the new state transition matrix will be p inverse of old state transition matrix times p. So this is also what? This is also like a diagonalization, like a thing, like this formula is looking like a diagonalization, right? So yeah, the STM changes. Okay, so yeah, that is what we did. So like one boundation in this p, right, the determinant can be 0. Determinant it should be a non-singular matrix, as I explained in the start of the previous lecture. So that was the basic revision. Now we will start the lecture 12b, where we will be again studying a bit of similarity transformation, and at the end we will be studying parallel and cascade decomposition. So as I mentioned earlier, right, that why do you do similarity transformation? Basically, a particular state space diagram or a system can be defined in many ways, right? State equation can be defined in infinite forms. Okay, but we have to already obviously choose minimal forms, but we have given few basic forms, standard forms, which we mainly derive to. So there are procedure for converting those to standard forms. So I will write the standard forms and I will show you how to convert to those standard forms, right? So similarity transformation have mainly 4 standard forms. Okay, this is wrong. It has 4 standard forms, right? What are the 4 standard forms? Like the first one, right? First one is controllable, canonical form. And this has also another name, that is a phase variable form. So you can remember that name also. But in short, this is written as CCF. I will write this is CCF in from now on, and this is also known as phase variable form. Okay, is it recording? Yeah, everything is recording fine. Phase okay. Now what is the second form? So second form is observable canonical form. In short, this is known as OCF. Okay, and what is the third one? Third one is the diagonal canonical form. And what is the fourth one? Fourth one is a Jordan. So it is just a bit of similar to diagonal canonical form only. There is just a bit of difference. Jordan. I have forgotten the spelling of Jordan. Canonical form. Okay. So right, what do you mean by canonical? So canonical, right? Canonical means the minimal set of variables. Okay. Canonical basically means the minimal set of variables. So this is what basically canonical means. And like this forms, right? Like these two, right? These two are different. In this case, diagonal canonical form, we have independent eigenvectors, and in Jordan canonical form, the eigenvectors aren't independent, right? So that's why if the system matrix don't have independent eigenvectors, then we use this one, and if they have independent eigenvectors, then we use this one. Okay. So yeah, this is just a basic difference. So diagonal, you understand, right? Diagonal means my system matrix will only become diagonal. Okay, diagonal matrix, other elements will be 0, only diagonal elements will be non-zero. So we want to convert it to that form so that we can get some information out of that. Okay, very important. So why we wanted to convert to all these things, we will understand in next few chapters. Okay, now another thing is that these were the forms, right? These were the forms. I will tell you like how to do these forms and what are the meaning of these forms. Okay, I will tell you. But what if I want to convert the transfer function? Okay, convert the transfer function to this form. How will I convert this? I have transfer function and I want to convert this to this CCF form. Okay, so how to do this? All these things we will do. So there is another topic known as decomposition of transfer function. So this we'll understand. So this is like mainly this is what we will do, right? This is what we will do. So this is the other topic. So decomposition. So those were the forms basically. Okay, by form, the A, B, C matrix, all those forms, right? That is the form. And now we have been given the transfer function, and the transfer function need to be decomposed to those form, right? A, B, C matrix. So I have to convert the transfer function to that particular state equation, standard form, right? So just watch through the video, you will slowly get the feel of it. Okay, position. Of transfer function, right? So like it is same only. So mainly it is, one is direct decomposition. Okay, direct decomposition to CCF, and another is same, like that directly will decompose the transfer function to CCF. How? I will show you. And directly will decompose the transfer function to OCF, right? To OCF. And there are two other transfer decompositions of the transfer function. One is parallel decompositions, and another one is cascade. So cascade is just a waste. Okay, it's very simple. But parallel, right? With the help of parallel decomposition, I will change the transfer function into diagonal canonical form. Okay, into diagonal canonical form. Or if we aren't able to change the transfer function into diagonal canonical form, then we'll change it to Jordan. Okay, so parallel is very, very important. So pay attention when I say about the parallel. Obviously these are also important. Okay, so let's first take an example to understand what is a canonical standard form. So let me take a differential equation, right? So example of controllable canonical form that I wanted to mention there. Controllable CCF, right? Example of CCF basically. So we have one, let's say we have one differential equation. D square by dt square plus d by dt plus we have y of t equals to e of t, equals to e of t. So this is our differential equation. So what I want to do is convert this into, like, write the state space equation in terms of CCF, right? So how will I do it? So for CCF, right, what do you do? Just what we are doing ever since the start of this chapter, right? What we are doing, that the output, right, will assume output equals to sum of the state, like some state variable. It will be x1 of t, okay, first state variable. Then the differentiation of the output will be x1 dot t, which will be equals to the second state variable, okay, which will equals to second state variable. And like the twice the differentiation, d square y of t by dt square will be equals to the x2 dot t, right? So like we'll have two state variables here because the order is 2. So we'll have two state variables, right? Order is 2. So this is how we're doing until now, okay? So now what is my x2 dot of t? So I will replace this x2 dot of t here, right? And this, right, I will replace this with x2 only because I want to write x2 dot of t in terms of x1 and x2. So this I will replace with x2, this I will replace with x1 and u, right? So I will get the relation of x2 dot of t. Everything else relation I already have. I have x1 dot of t as a function of x2. I already have y as a function of x1. So I only need x2 dot of t as a function of x1 and x2 and u, okay? So yeah, so replacing in this equation, this is x2 dot of t, this is x1, and this is this is x2 and this is x1. So this becomes x2 dot of t, okay, plus 2xt plus this is x2t plus 2x2t plus x1 of t, okay, equals to 0. This is 0, right? Yeah, sorry, this is ut, sorry, this is ut. Now I can write x2 dot of t in terms of x1 and x2 itself, the state variable themselves. This is u of t, right? So yeah, now like I can directly write the CCF form. So this is the CCF form, right? The matrix format basically. So this are my state equations. So this is x1 dot of t, x2 dot of t, okay. And what is the matrix? So matrix, right, with x1 is only related with x2, so this will be 0 and this will be 1, and x2 is related with -1 times x1 and -2 times x2. This is x1 x2 of t, and this is 0 1 ut, okay. And what is this? Y of t, right? How is y of t related? So y of t is simply equals to x1 t, right? So this will be 1 0 and x1 of t and x2 of t. Now, right, can I write the transformation directly from here? So what you observe is, like, this is a standard format where what happens is the rows start with, like, if I have 3 cross 3 matrix, it will start with like 0 1 0, then 0 0 1, and then at the end row, right, the end row will be the coefficient of the new denominator of the transfer function, okay. I will write all this in like when I'm explaining the controllable canonical form, I will write the standard forms, okay, don't worry. So yeah, that will happen. And for this one, right, this this will be in this form. So if I have a 3 cross 3 matrix and I'm converting it to a controllable canonical form, it will be 0 0 1, okay. All the rows will be 0 except the last row, and for output, right, all the columns will be 0 except the first one, okay. First column will always be 1, Okay, that's how we do it, right? Because that's how we define, right? Y of t is always equals to x1 of t, and u of t is always related with the last state variable. Okay, and the other state variables, it is not related, it is a 0. Okay, so it is very important. So yeah, this was it for that. And now one thing you observe, like I have as I was saying, that the coefficient of transfer function, I will come to that. We have been given only the differential equation, so I will not come to the transfer function yet. Okay, when I will be doing the decomposition, parallel decomposition, there I will explain all these things, right? So this was one question. Now this is the actual question. Okay, this is some actual question. So a system has state equation output given below, x1 dot of t and x2 dot of t, like this one. Okay, 1 0 and 0 1. Okay, this is definitely not our CCF format, right? CCF form. But what this is asking, convert this into controllable canonical form and also derive the state diagram. Okay, how will you convert this into controllable canonical form? Okay, just think, how will you convert this into controllable canonical form? So I haven't taught yet, so you can't think. Okay, so what we have to do is, first, like what you can do to convert into controllable canonical form, you can multiply the system matrix with obviously that P matrix, right? P matrix, and do similarity transformation, and from there you will directly find the controllable canonical form. You find the P matrix. Okay, you multiply with P, like P inverse A P, do that, then now C changes to CP and B changes to P inverse B. Okay, if I able to find P, then I can directly write this state equation right here only, right? Only if I find P. But finding that P, right, is very difficult, that's why what we will do, we'll go from the transfer function method, right? First I will decompose this into transfer function, then like I will find the transfer function, then I will decompose the transfer function to controllable canonical form. Okay, how? I will show you. So here, right, step 1 will be and step 2 will be decompose the transfer function to controllable canonical form. So what will be my transfer function? So as I told you, right, something you have to mug that up. So again, let me tell me the formula. So what will the formula? Formula will be C times Si minus A inverse. Okay, Si minus whole inverse, Si minus A whole inverse into B, and we have plus D also, don't forget that. Okay, so we have okay, Si minus A inverse B plus D. Okay, so this is my transfer function basically. So like my T of S, right, what will my T of S? So C, right, what is C? C is 0 1. Okay, C is 0 1. What is my Si minus A inverse? So first I will write this is S plus 1 S minus 2, S plus 1 minus 2 S plus 4 and this is whole inverse. What is B? B simply equals to 1 comma 1 0, right? B is simply equals to 1 0. Okay, and we have D also. Is there a D? D is 0 in this case. So yeah, you are lucky if you forgot the D. So D is 0. So what I will do, again, do that ABCD, right? This is 0 1 and 1 0, right? So I will do that ABCD, so it will be easier for me. So if I do here ABCD, this is 0 times A and 1 times C, right? So I'm left with C in this matrix, and 0 times B, and this is D. So C and D, then C and D is 1 comma 0, so C times 1, D times 0, so I am left with C only. So C is here only. So what will be my value, right? What will be my value? So this is okay, this is my minus 2 only. So if I do inverse here, this changes to S, this changes to this swaps out, right? This main diagonal element swaps out, and we just change the sign of the we just change the sign of the diagonal elements, right? We just change the sign of the diagonal elements. So this becomes plus 2, and we are dividing with this one. Okay, let me write this here. This is 1 comma 0. So yeah, this is my transformation. So again, what I told, right, I will only get this element. So what I will get is, this will be equals to 2 by s plus 1 into s plus 4. So this becomes s square plus 5s plus 6, s square plus 5s plus 6, right? So this is what I get in the denominator. So now what is the interesting thing that I will do? So what I will do is multiply the denominator numerator by the I will take common the numerator denominator by the highest power. Okay, what I will do is take common. So this will be 2s raised to the power minus 2. Okay, and like this will be 1 plus 5a raised to the power minus 1 plus 6a raised to the power minus 2. So again, right, if we do like if I take the highest power common here, so common a square. If I take the highest power, not the denominator numerator, totally wrong. I have to take common of a square from the denominator. I take common wherever. If it is in numerator, then it's fine. If it is in denominator, then it's fine. But for actual realizable systems, always the order of the poles will be higher. Like the order of the denominator will be higher, greater than the order of the numerator. Number of poles will be always greater than number of zeros. So we have to take common of highest power from the denominator itself. If I take common from the denominator, right, that will go above. Okay, I took s square common here. This square goes in the numerator as s to the power minus 2, and here I have this equation, right? Now, right, my y of s and u of s is in terms of this. Okay, y of s and u of s is in terms of this. Now what I'll do, I will multiply a dummy state variable x d of s, both numerator and denominator. So what I will do, okay, I had to like this was step 2 actually. Convert to CCF. Multiply dummy variable to both the numerator and the denominator. Multiply dummy variable to both numerator and denominator. Okay, so yeah, so what I will do, like dummy, okay, dummy, not dummy variable, dummy state variables. I should write this as dummy state variable. Okay, let me change this here. This is okay. So what is y of s over u of s? What is y of s over u of s? So y of s over u of s, right? So what I will do, I have multiplied it with dummy variables. So let me copy this. Okay, copy this. From the transformation also you can directly write the state equations, but as the question has asked us to find the state diagram also. So we'll you use this. So for finding the state diagram, you have to use this. So xd of s and xd of s. Okay, so what I can do now is I can write my u of s like this. My u of s will be equals to 1 plus, like 1 plus 5 s inverse plus 6 s raised to a minus 2 xd of s, and my y of s 2 s raised to the power minus 2 into xd of s. Okay, so yeah, that is what basically I am doing. So as this is a second order system, so I will have two integrators, right? Now I will make the state diagram basically. So first what I will do, I have two integrators, right? So I will place the input here as usual at the left, place the output here at the right, and I have two state variables. So I will have two one-way terms, and those will be directly connected, right? Directly connected. Okay, because like what we should do, that x2 dot x1 dot is equals to x2, that we should do, right? So that's why. So this is equals to 1 by s. Now what I will do, now I will assume my dummy state variable. My dummy state variable will be here on the left hand side. So this will be my xd of s, and this, what will this be? What will this point be? This will be 1 by s inverse times xd of s. So this will be s inverse xd of s. This will be s raised to the power minus 2 xd of s. So okay, I let me not write xd of s, so you will get confused. So yeah, this is basically what I am here until now. Okay, now right, as u of s is denominator, now I will write xd of s in terms of all these things, right? So let me copy this. So what I will write is like, okay, let me understand you. So I need, what do I need? I need xd of s in terms of other variables, right? In terms of other variables. Here I need xd of s in terms of other variables. So I will like expand this. Let me, step 3 state diagram. So this xd of s equals to, like, let me write this in here only. So plus xd of, so let me not write s, so you will get confused again. So it is a function of s, that we know. Okay, no worries. So this is 5 times s inverse. Okay, let me put the s inverse and 5 on the outside. Okay, and this is 6 xd s to the power minus 2 equals to u of s. Now I will again copy this whole thing, and now I will write the relation for xd of s. I will take this one, right, this on the right hand side. So my xd of s, xd will be in terms of, let me delete this, xd will be in terms of the other state variables. So basically these are my other state variables. You are not understanding, just it's hidden, right? So this is minus 5 s inverse minus 6 xd s minus 2 plus u of s. So I have minus 5 times this xd of s inverse, so I have to bring one loop here as minus 5, right? So let me, okay, put this over here. Let me reduce the size. Let me put this over here also. So this is minus 5. Okay, now right, Now I have minus 6 times xd of s to the power minus 2. So again, let me keep this over here. Okay, let me color this also. So let me color this green, let me color this green, let me color this green. Okay, green. So this is minus 6, right? So a minus 6 also will come. So let me get this over here. I can reduce the size, fine. This is minus 6, right? So yeah, now right, and we have also 1 times u. So input is also connected here, right? So input will also be connected. Okay, so this is my state diagram. Now I have to connect the output also, relate the output also. So what is the output relation? So now this was the state relation, so I'll load the output relation. So my output relation, right? So my output relation, where did it go? So I wrote it here, right? It was here. Yeah, I have to copy this one. Output relation is like this. It is 2 times s in s to the power minus 2 xd of s. So this is my output relation. So this xd raised to the power minus 2, it is 2 times this. So what I will do, write this over here. This is 2 times, right? This is 2 times. Okay, so this is my output relation basically. Now this is my like state diagram. Okay, now let's write the state equation. So what will be the state equation basically? So first what I will do is remove the one by terms. So again, like, let me copy this and also write the state variables. So this time I will write the state variables. That was a dummy variable. Now I will write the state variables. So I'll delete all this, okay. I think this is a step 4. Write the state equation. We could have done it directly from the transfer function also. How? I will show. So like, yeah, let me assume the state variables like this x1, this one will be x1 dot, and what will this equals to? This will be equals to my x2. Okay, and this one is x2 dot, and what will be this equals to? This will not be equals to anything. This will just x2 dot. Okay, so yeah, now I have to remove the one by terms because I have already taken the effect of using this dot, right? Dot representation. So we'll remove. Okay, if I remove this, okay, the whole thing goes off. Okay, that's fine now. Whole thing can go away. Okay, that's fine. So yeah, so we are only left with this. So now simply let's just write the relations, right? We have been doing this since ages. So do it now. Okay, solve it. So after that, see my solution. So yeah, that's what you should do. You should do it by yourself. Do everything by yourself, right? Then you see my solution. So x1 dot, what will be x1 dot equals to? So like one thing, like again, one mistake is that like when this is equals to this, right? So what you have to do is we have to make another node just to be on the safer side. So this will be my x1 dot and this will be my x2. Okay, and this is gain is 1. Okay, just to understand that x1 dot is equals to x2 actually. Okay, else if I just delete the node, then that node is also gone. Okay, so that's why. So x1 dot equals to x2 itself, and x2 dot, right? x2 dot equals to x2 times minus 5. Okay, minus 6x1. And what is y? Yt equals to 2x1. So this is basically, let me rewrite it. So this is right. Minus 5 to minus 6x1. Okay, so yeah, this is what my x1 dot and x2 dot is. So yeah, let me write the state equations in matrix format. So x1 dot, x2 dot. So this is basically 0, 1. That standard form, right, that we saw. Now this is minus 6 minus 5, minus 6 minus 5, this is x1 x2. Now b has also a standard form, right? What is the standard form? B is 0 0 0 0 1. So like okay, I forgot something, sorry sorry. So here, right, we have u also. I know you are screaming u of t also. So this, right, this I need to convert into y of t and u of t. So like this, these are understandable only. I hope you understand. This is y of t. Okay, so sorry, I forgot a u of t here. So this type of silly mistakes may happen sometimes. So yeah, this is x2 dot of t. So it will be 0 1 and u of t. Okay, let me write this in full white only. And now what is my y of t? My y of t is 2 comma 0, right? 2 comma 0 into x1 x2 and d is 0 only. So if I write the transfer function, then from there you will understand. If I have the transfer function, right? Yeah, not this one, this one, right? This transfer function, copy and paste this one. So you could have written it directly here. You could have written the canonical form directly here. Okay, because the question has asked us to find the state space diagram. That's why we draw the state space diagram, and from there I wrote the state equation. But from here you can go from here to here directly. Okay, how also one more thing is that as they haven't told us anything about the transformation matrix or the P matrix, right? That matrix that we use to diagonalize the A or something, or transform the state vector, state variable, basically P, like our old x equals to P times x bar. They haven't told us, we won't use that, and most cases we won't use that. Okay, just for theory and knowledge I have to tell you that, and that may come in handy in next few lectures. That's why I have to teach you all those things about similarity, transformation, all those things, right? So we won't use the similarity transformation. We'll always, maximum cases, we'll always use this method that I used here, right? So just step 1 was like the first to find the transformation. Okay, then convert it into CCF. How? I take common of the highest power from the denominator. This goes above and below, then I multiply by a dummy state variable, and from there I draw the state diagram. Okay, or from directly the transfer function I can directly write my controllable canonical form. How? So here, right, what you will see is that for the controllable canonical form for CCF, basically A will have a standard form. Okay, B will have a standard form, and C will depend on the numerator. Okay, depend on the numerator. Okay, numerator of what? Transfer function. Okay, so this is what ACCF means. So let's say I have a I already explained to you also, I have a transfer function of this, right, third order s cube. Like this coefficient should be 1, highest power coefficient should be 1. Okay, s cube plus c1, no, not c, okay, this should be, yeah, c2 of s square plus c1 of s plus c naught, right? And let me name this as D. Upper side I have D. Okay, so how will my basically transformation look like? So my transformation, right, sorry, how will my A matrix look like? So my A matrix will look something like this. First of all, this is a third order, so my A matrix will look like something like this. It will be 0 1 0. Okay, then it will be 0 0 1, and the last row, right, last row is very critical. Last row will depend upon the coefficients sorry, I was checking is if it is recording or not. Coefficients of the denominator. Okay, coefficients of denominator. Okay, so what will be this? So this one, right, this one will go like this is going from here, so I'll go in opposite direction, and in the writing the negative sign. So this will be minus c2, minus c1, and minus c0. Okay, so let me like give this a bit of space. Actually, this is up here, this is up here, this is up here. Yeah, now it is fine, and this is in the bottom. Okay, so yeah, this is how I will write, right? This is how my A matrix will look like. Now how will my B matrix look like? So my B, right, B will be like this form. If like this is a 3 cross 3 matrix, so my B, right, I can write this here only. Okay, I cannot. So B will be like this. All the elements will be 0 except the last row. It will be 1. Last row will be 1, right? Last row will be 1. Okay, so what will be my C basically? C, right, let me change this in some more easier format. So if C is like this, this is plus S D1 and plus let's say S square D2. Okay, then my C, right, C will be like this. It will be D0, D1 and D2, right? So my C will be like this. So we'll go from, if I am going from here to here, so we'll go from here to here. Again the direction will change, right? Okay, now let's solve the next question. So the next question, right, yeah, we have this question. So this question is the same only, just the difference is we have to convert this into a observable canonical form. Okay, now you try to do it. Okay, then I'll solve. Obviously you won't be able to solve because you don't know, but the procedure is similar only. In observable canonical form, the A and C are in standard format. So again, step 1 is find transformation. So the transformation we have already found out, so I will just copy and paste. Yeah, this one, right, this one. Where is it? Yeah, here. Previous question. Okay, transformation is from previous question. So this is my basically transformation. Now what I will do, again multiply, like divide by the highest power. Okay, like, or like take common of the highest power. So again, right, so this is basically my y upon u. So y upon u, right, is equals to, so this is my 5s inverse plus 6s minus 2 equals to 2s minus 2. Now right, what I will do, I will write y in terms of other variables, right? I will write y in terms of other variables. Okay, so this was u of s, this was u of s. Okay, so this is what, right, this is y of s plus 5, like I will take the y of s only and move other terms on the right hand side. So this is again y of s 5s inverse plus 6s minus 2. Okay, this is u. Okay, so what is this? So this, right, this is equals to 2s raised to power minus 2 u of s minus y s 5s raised to power minus 1 plus 6s raised to power minus 2. Okay, so this is why this is what my y of s is in terms of these two, right? So what I will do is now draw the state diagram. Okay, okay, draw the state diagram. So first is like order is 2, so 2 indicators. Okay, 2 indicators, but this time, right, I will not connect indicators back by back. I will connect them with a gain of 1. Okay, that is the main difference between that and this. Okay, that is the main difference. But there also we have to do that that x2 dot equals x1, that we have to do, right? So here we won't connect the indicators back to back. That is the main difference. But we will have 2 indicators, so obviously we will have u of s over here and y of s over here. Okay, we'll have 2 indicators and a gain between them. This is step 2, right? This is step 2. So this is basically what my state diagram is. Now what I'll do, I have to write the relation between input and output. So right, first thing is I will copy this again. Okay, copy this and write that equation, right? Take that equation also. If I take this equation, right, so what do I see? First I will write in terms of u of s only, u of s only, right? First I will write in terms of u of s. So what do I see? U of s, in terms of u of s, I have 2 of s inverse times u of s. So there will be some direct interconnection. Okay, so what I will do, firstly I will make this gain as 1. Okay, this gain I will always connect this gain as 1, and what is this, and I will connect this one also. Okay, connect this one also. So now, right, I have to put some gain over here. So if I go from u of s to y of s, I have 2 as gain, right? 2 as the factor, right? So this is 1 only, this is 1 only. Like this is what, like this is like, let's say this, name this as g, right? G, this is g u of s, g u of s. This becomes s inverse u into g, and this becomes s minus 2 u into g, right? So yeah, so what what do we need? So s inverse s to the power minus 2 into g should be equal to 2 s to the power 2, right? So s to the power minus 2, so g should be equal to 2 basically. So from there I understand the g is equal to 2. Now let's go to the next slide, and there we'll understand what else we need to add. So we're going step by step. So now, right, now what we need to add? So now we have to add this, this part, right? This portion is done. Now this portion. So one thing is, what is this this part? This is, if this is y of s, right? If this is y of s, what is basically this portion? So this portion, right, I have to take this from here, and if I multiply y of s from here, I should get this one, right? So this is, okay, let me explain, let me draw this, then I will explain it to you. So as I am not able to draw, right, so I am not able to explain it to you. So I may take y of s over here, okay, and this, okay. Then if I put a gain of minus 5 from here, what do I see? What do I see? So this y of s times minus 5 times s inverse equals to this, right? So it is getting added over here. So yeah, that is what this is. Now one more I need to add. What is that? This one, right? This one I need to add. So again, let me copy this. So this one, right, which one I need to add? So this one, this part I need to add. Again, if I do here minus 6 from here to here, right, minus 6 from here to here. So what do I see? If I multiply y of s times minus 6, okay, times s inverse, so minus 6 s inverse y of s, then minus 6 s to the power minus 2 y of s, which is equals to this. So this is getting added here. So 3 things are getting added. This u of s is getting added, this is getting added, and this is getting added. You write the Mason's gain formula, right, of y of s in terms of this point this node and this node and this node, right? All these 3 nodes. Okay, so from there you will understand, yes, you're correct, like this y(s) is coming over here and over here and over here. So we have 3 forward paths, right? We have 3 forward paths. So yeah, that was the basically the state diagram. So this is the state diagram. Input and output we have we don't have any state variables, like we don't like write any state variables here. So this is the state diagram. Okay, now what we'll do, we'll write the state equations, right? State equations. So this time, right, again I will assume like state variables. So what I will do, this was a step 2, right? State equation is a step 3. Okay, so let me paste this over here. So what will be this, like I will convert this in time domain, right? Will not make that mistake again. This will be u of t, this will be y of t. Okay, and let me assume this as x1 of t, right? X1. So what will be this one will be x1 dot. Okay, and this one won't be x2 this time, this will be x2, this is x2, right? And this is x2 dot of t. Okay, now I have taken into effect of the 1/s effect, so I will remove the 1/s terms. So what do you have? So yeah, now what I will do is write the state equations. So what I can do is directly write the state or like a matrix by just seeing, right? So this you have to get used to, like this is how you will actually solve in gate examination, not the slow way. Okay, that was just for teaching you so that you get used to it. So now you have to write it with fast. So how will you write it with fast? This one is x1 x2, this one will be my bu. Okay, this is y of t, and this will be my c x1 x2. Okay, so now let's see what is like incoming to the x1 dot. So x1 dot is here only. Okay, so I will write it in terms of state variable. So x1 is here, so x1 times -5, so it is -5 x1, so this will be -5. Okay, and then what is like x2, yeah, it is directly related with it, so this will be 1, right? So it is x1 dot equals to x2 times 1. Okay, so 1, so that's how you directly write it. Okay, now we have x2 dot, right? X2 dot, so we are coming from x1 to into -6 into x2 dot, so we have here -6. Okay, this is x1, right? So -6, right? I hope you're understanding. This is x1 into 1 into -6 equals to x2 dot. So x1 will be like multiplied with this term, right, with this element, so -6 will come here. Okay, so then I have x2, but I don't have any forward path. Okay, this is open and this is in the opposite of the flow, so this is 0 only with respect to x2, 0. Now with u, right, for u x1 dot is not connected with u, so it will be 0 for x1 dot. Okay, for x2 dot it is 2 times u, right? 2 times u. So yeah, that is what this is, 2 times u. Now this x1 equals to y only, x1 into 1 equals to y, but nothing else is coming. x2 is can't come to x1. Okay, and u also can't come to, sorry, not x1, u also can't come to y, and x2 also can't come to y because they are not connected. Okay, they are in reverse direction. So I hope you understand. So only we have x1 and this is 0. So what we can see is like two matrices are in standard, right? A and C. Like how is A in standard? I will show you. Okay, so yeah, let me first like tell like the standard form. So for, we could have directly converted the transfer function to this. For OCF, A will be in standard form, and what else will be standard form? C, right? C will be C will be in standard form. Okay, so C will be in standard form. So what will be the standard form? Let's say I have a transformation, right? I have a transformation. Okay, I have a transformation like this, which is let's say some numerator, and in the denominator I have s cube. Okay, let me take it like this only. Let me take this example only. Let me copy and paste this. Where is the transformation? This one, right? This one. Let me. So my A, right? A will obviously depend on this, on these terms. Okay, so the highest power will come over, like come on this side. Okay, that is this one. The coefficient of this one won't come. This will come and this will come, and the last term will be like this will be on 2 cos 2, right? So last term will end on there, like A0 will come here. So how can I write this? So this I can write like d by s square plus d1s. Okay, not d1, I should write this as c1s plus c0. Okay, so here, right, the negation of c1 will come and negation of c0 will come. Okay, and after this we'll get a 1, and this will be 0. Okay, this will start up like 0, and then this will also be 0, and this will be 1. Okay, so yeah. Okay, no, sorry, so we don't have like this is only 2 cos 2, right? So for example, let's say if this is a 3 cos 3, then what will happen? So let me write this like directly here. So I will take an example for 3 cos 3. Okay, this is -5 and sorry, this is 6 and -5. So this is, sorry, again I'm doing wrong. Okay, this coefficient, right, this coefficient, this is the highest power coefficient and this is the lowest power coefficient. It will come in the bottom, right? So this is how you remember it. Now like what will be my C form? So C, right, C will always be something 0 1. Okay, for 2 cos 2, for 2 cos 2 in this case, right, as you can see here, C came as, okay, yeah, C came as 1 comma 0, right? So that is for 2 cos 2. यार ये क्या हो रहा है? ये क्या हो रहा है भाई? ये वो ऐसा आएगा, ये वो ऐसा आएगा, ये क्या हो रहा है? सीधे सही 1-0 हो रहा है तो गलत, उल्टा बोल दिया. So how will my C come? C, right, C will always come like this, standard form, right? And how will my B come? B, right, B will depend on the numerator. Okay, B will depend on the numerator. Okay, so yeah, this is what basically my ABC will be. So let me write it for 3 cross 3. From there you will better understand. So for 3 cross 3, right, so why B depend on the numerator? So basically for this case, right, so if I write the B, okay, let me first write take the transformation here again. B is plus 2, right? So B is plus 2. My B will start from basically from 0 and end at 2. So B, right, this will be 0 and here I will get 2. Okay, due to this 2. Okay, as like s to the power 1, s1 has 0 power. So again, right, if let me take for 3 cos 3 matrix, there you will understand better. So my T of s equals to, let's say, d1s plus d0 s cube plus c2s square plus c1s plus c0. So what my A matrix becomes? So my A matrix, right, it will simply become all these coefficients st of s minus c1 minus c0, this will be 1, this will be 0, this will be 0, this will be 1, this will be 0 0. Okay, so yeah, that's how my this matrix will become, right? This matrix will become. Okay, now right, if what will my C matrix become? C matrix will be 1 0 0. Okay, C matrix will be 1 0 0. And what will my B matrix become? B will depend on the numerator. So what will happen? There will be no sign change, right? So there will be no sign change, and it will start from the highest power. This will be D1 and this will be D0. Okay, so that's how my D matrix will become. Okay, so you solve for it, and check whether this is coming for a 3x3 case, right? If you convert it into OCA form. Okay, so yeah, we'll lift with parallel and cascade decomposition. So this lecture has gone already like 1 hour. So in the 13th lecture, I think we'll do parallel decomposition and cascade decomposition. Okay, and from there we'll understand few more things also. So yeah, thank you for